Right, so hi everyone, and welcome to the weekly CosmoQuest Science Hangout. Today it's hosted by me, Emily Lakdawalla of the Planetary Society. You might be used to seeing Pamela Gay here. I was kind of out of it for a few weeks, but now I'm back in action. And my guest today is Dan Durda of the Southwest Research Institute. He is an asteroid scientist, astronomer, chaser, as well as a space artist. And so our conversation today is no doubt going to be wide-ranging. So I would like to ask those of you who are currently watching this to please +1 it on Google+, or give it a thumbs up on YouTube. And we'll go ahead and get started. And Dan, I'm wondering if you could just give us a little bit of an introduction about what exactly you do, what kind of asteroid research you do.
Great, sure. Glad to be here, first of all. Thanks a lot for inviting me for this. So yeah, I like to tell people that most of my research is centered around making molehills out of mountains, because I started actually into the asteroid game looking at the collisional evolution of asteroids. So that was in grad school, but let me back up even before that. I've been a scientist literally all my life, right? Even as a little 5-year-old, I think that was the beginning of all that curiosity. I grew up on nature documentaries on TV, and I think some of my favorites actually were the undersea world of Jacques Cousteau. So I was actually, for quite some time, I was really convinced I was going to be a marine biologist, and it was this very interesting television show that came out in 1980 that revamped all my interest in astronomy. It was Carl Sagan's Cosmos, and that really redirected me, because really for me, I think it was the vision of a universe just full of habitable planets and extraterrestrial life really actually focused me in astronomy.
And you know, it's kind of amazing, because when it came out in 1980, we had no idea if there were any other solar systems in our galaxy, and
absolutely.
And now 30 years later, there seem to be planets everywhere. We don't know if any of them have life on them yet, but there certainly are a lot of possibilities out there.
I wish Carl would have lived to see that, because I think he would just be absolutely reveling in this. And I remember that was part of forgot which chapter it was in the book, but in which episode it was toward the end. He introduced this sort of the concept of this Encyclopedia Galactica, and I remember all these entries showing all these potential planets with that just caught my imagination. And so all through undergraduate school, when I went to the University of Michigan, really a lot of my focus was on the search for extrasolar planets. Still a little bit ahead of its time at the time, but that's where my sort of started focusing in. But when I went to the University of Florida for grad school, my advisor had come from Cornell, and he was actually one of the discoverers of these bands of dust that we see superimposed on the background zodiacal cloud of interplanetary dust in our solar system. And he had actually used data from the infrared astronomy satellite that was launched back in 1983 to make a connection between those bands and clumps or clusters of asteroids out there in the main asteroid belt between Mars and Jupiter that look to be collections of fragments of asteroids that are the collisional remnants of the breakup of larger asteroids. And so I did my thesis work on that, and have been really working on asteroid collisions and impact craters and all that other sort of violent stuff in the solar system ever since. So
you must have been pretty excited to see the pictures of Vesta that came back from dawn recently.
Yeah, absolutely, absolutely. Lots of, I mean, Vesta's this really amazing, interesting, in-between world in the context of the smaller asteroids, which are really sort of the fossil remnants of the planetesimals that were that accreted to form the planets in the solar system, and the larger objects that have actually accreted to form, things like terrestrial planets. And Vesta and Ceres, the two targets of the Dawn mission, are these really very scientifically interesting sort of transition worlds. They're not quite full-blown terrestrial planets, but they're not mere planetesimals either. And so they're particularly valuable sort of tests of the various hypotheses we have of the formation and the evolution, the subsequent evolution of these objects in the main asteroid belt. So Vesta is one end member. It's big enough to have actually melted and differentiated. We know it has a basaltic crust, and the data that's coming back from Dawn now are seemingly reinforcing this idea that it's differentiated into a sort of a core mantle crust structure. And yet, we'll find out more when we get to Ceres in a couple of years, but the indications are that Ceres, for some reason, is not differentiated, even though it's actually slightly larger than Vesta. So these are the interesting puzzles that are going to be hopefully answered and revealed, and maybe even more interesting questions raised by the Dawn mission.
Although we know already that Ceres is substantially more round than Vesta, and they've even seen water on its surface. So I don't know. I'm quite excited to see what Vesta's actually, I mean, Ceres is actually going to look like when we get up close to it.
Yeah, absolutely, absolutely. All these worlds, it's, you know, we've never seen something like Ceres before. It's actually one of the more primitive end members of the compositional type of asteroids, and certainly something in that size range. You know, Vesta itself looks a little different than some of the smaller asteroids we've seen. It's heavily cratered, but there's different style, different look of geology on the surface of that object. And with Ceres, it'll almost certainly be yet another surprise for us, and yet another unique object. I mean, the asteroids are like people. I mean, as a general class, they're all sort of similar, you know, but individually, they're all individuals. So
and each with unique histories for also.
Absolutely, absolutely.
If you're, I should stop. If you're just joining us, I'm Emily Lakdawalla of the Planetary Society, and this is Dan Durda of the Southwest Research Institute. We're on the CosmoQuest Weekly Science Hour, and talking to Dan Durda about his work on asteroid research. And I'm curious, how do you do your research? I don't think you're on spacecraft instrument teams. Or do you primarily work with telescopes, with astronomy spacecraft, or how do you do your work?
And that's a great question, because of the whole range, as you alluded to, for folks to study these things. My background was really primarily focused as you know, sort of a numerical modeler, and so a lot of the work I do are models of the collisional evolution. So treating the whole collection of asteroids out there in the main belt as sort of this big bag of rocks that mathematically at least jumble around together and collide and grind to form a distribution of sizes with a lot more small objects than there are big objects. And the understanding that collisional evolution, looking at the distribution, the details of the distribution of that size assortment, can actually tell us something about the actual physical properties of the objects and the way they break apart. So that's one aspect of the modeling. It's sort of numerical, or of the research, numerical modeling. But I do a lot of laboratory experiments as well. I mentioned that a lot of my interest is in the impact physics, the breakup, the cratering mechanics of asteroids, and so I've done a lot of my research actually in the laboratory. Significantly at the NASA Ames Research Center, where they have a large hypervelocity gas gun. It's called the AVGR, the Ames Vertical Gun Range. This was a facility that was actually built back in the 1960s, primarily to start to study and better understand the physics of impact cratering as we were getting ready to explore the moon. And it's been used over the years for a lot of other impact applications as well, but for me it's been working with my colleague George Flynn at the State University of New York in Plattsburgh. We have a project to actually look at the impact disruption of real actual meteorites, real samples of asteroidal material, to look at the formation of interplanetary dust particles and how those are related back to their parent bodies, the meteorites and then the asteroids.
I want to talk more about the vertical gun range in a minute, but first I would like to explore, it's one of those words that means quite different things to scientists than it does to the general public, and that's the word model.
Oh, yes.
I'm wondering if you could explain to us what you mean when you say model and modeling. What are you doing when you're doing that?
Yeah. Well, you know, it actually, for our use, sometimes it can actually mean a similar thing in the quote-unquote everyday world out there. Instead of being literally a physical model, you know, some sort of representation in space out there of a version of some other thing you're building, a model plane or a model car, we often in science will reproduce the behavior of phenomena out there with, you know, computer code. Literally just, you know, a lot of equations of the physical behavior or something converted into, you know, lines of computer code that then go through and iterate and reproduce as best we can. You can only do these sorts of simulations as well as you know the physics to put into it in the first place. It's literally a garbage in, garbage out sort of thing. But in that usage, the term model is literally just the lines of computer code and the simulation that is run to look at the output of some event that we can't normally, because it maybe takes too long or has a size scale that's too large for us to reproduce or too small for us to reproduce directly in front of us in the laboratory. So it's a simulation, a computer simulation.
I think one of the things that I discovered as a graduate student was just how amazingly you can reproduce the behavior of entire planets by writing down just a couple of differential equations.
Yes.
So it's kind of cool how just a few lines of computer code really describing either exact or approximate solutions to a couple of differential equations can really reproduce some pretty complex behavior.
Absolutely, absolutely, and that's the power of being able to do these models, is to these computer codes, these computer simulations, is to run those, as you mentioned, sometimes rather simple models, but with rather sophisticated outcomes and ability to interact and test hypotheses. And the joy, the beauty of that, as I said, is you can actually run, you can in a sense run experiments numerically and run through a bunch of cases that would again either take too long or just literally be physically impossible in the real world, because you're simulating and examining phenomena that take, in some cases, literally geologic timescales to roll out. So,
and I think one of the other powerful things that I found you could do with it is that you could sort of explore the envelope of possible physical properties like densities and sizes and masses and numbers of particles and things, and see which ones actually matter to the history of something instead of some of them really wind up not mattering very much, surprisingly.
And you learn something from that, right? Because you, I mean, the same thing is done analytically for, if you are very good at analytical expressions, you can actually do a lot of this similar sort of thing with dimensional analysis and very simple analytical expressions that will also show you the root behavior, which parts of the physics, the phenomena that are going on, are most important. I'm not that good analytically, so I like to make the computers work for me. But,
yeah, I had a professor at Brown named Mark Parmentier who was famous for being able to do that kind of stuff. And of course, as part of his analyzing of equations, he would always come out with things like well, pi is about 2, so we can cancel this. And
it's a famous way to. That's right. I'm a pilot, so I do a lot of this sort of thing. As you were at Space Fest. We were at Space Fest together. I drove down from Boulder, Colorado, where I'm at right now, down to Tucson. It's a long road trip. And one of my space art colleagues, Mike Carroll, drove back and forth with me, and he was kind of, I guess, amused at some points at some of the little numerical games I was playing in my head to calculate estimated times of arrival and so on. And we got to discussing that. It's a very useful skill to have to do a quick dimensional check of some problem you're working through. At one point, we were watching a windmill, a wind turbine in northern New Mexico. And as I was watching these huge blades turn, the thought occurred to me, is like, God, I wonder how many G's of acceleration are going on the tip of the blade of this thing. And so I started going through. It was like, it looks like it'd be about a 200-meter radius on the blade, and kind of counted its period to be about 5 seconds, and just was running through. And at first, there was one particular very simple physics formula I couldn't remember. I thought I remembered what it was, but then I wasn't exactly sure. And so the only way I had to check to see if I was even close is I started thinking, well, is it even dimensionally correct? Am I coming out with the right units at the end? And so it's a useful skill to have, but when I can't do that, I just feed the raw materials to the computer to make sure they do it right. So.
I have a similar story. The last time I had to go to the Department of Motor Vehicles because I'd lost my license. California has this numbering system where, they call out numbers as you came in, and so I actually produced a spreadsheet and graphed and did a least squares fit to the times that each of the numbers were called, and so I was able to predict within 5 minutes when my number was going to be called, about an hour and 5 minutes in the future, as it turned out.
Right, very good. In fact, that's the same kind of thing I was doing with Mikey as we were driving across the state. I was trying to figure out roughly our time of arrival at Tucson. I got it within about 5 minutes. It was pretty good. But I said that came from my skills as a pilot, right? It's one of the things you do in pilot training. It's one of the very earliest things you learn are some of the very basics of navigation, and you have to. When you're up there floating around in the sky, you don't just pull over if you run out of gas. So you got to be always watching your times of arrival and what your fuel burn rate is, and it's a good skills to have.
All right, so let's get back to the vertical gun range, because that was also another great discovery in grad school, was this awesome instrument that you can fire things at several kilometers per second at other things and see what happens and film it. Right, exactly. And the reason it's so useful for us, it's a beautiful coincidence of the physics of that gun and the celestial mechanics of the main asteroid belt, that the speeds that you can shoot projectiles, little metal BBs, typically maybe either 1/8 of an inch across or 1/4 of an inch across, we can launch these things with that gun at typically 5-ish kilometers per second. That turns out to be because of the crossing speeds. The asteroids are out there like traffic on a busy highway, driving around the sun in these independent orbits out there in the main asteroid belt. But because of their
shaped orbits, their eccentricities and inclinations, they're crossing lanes with each other all the time. And the typical crossing speeds, the relative speeds of the asteroids out there, are about 5 kilometers per second on the average, which is very comfortably right in the range of speeds of the Ames gun. So it makes it perfect for us to just, you know, shoot and simulate those sorts of the impact physics out there. So it's just great. Looking to go out there again at the end of the summer. I've got 2 projects out there. It's 2 investigations wrapped into the same general project. In addition to shooting the meteorites and looking at the dust production, I'm also really interested, again because of my interest in the surfaces of asteroids, understanding the geology of what goes on those surfaces. You look at asteroids, they're rocky and blocky. It's broken up rock from other previous impacts. And a lot of what goes on the surface of these things, there's chunks of rock and block that are themselves the targets for being hit by smaller projectiles. And so I want to understand the morphology. What does it look like when a block on the surface of an asteroid gets hit by a small impactor? And what's that transition in morphology, the way things look from having the block being cratered and broken to being really broken apart badly, to the impactor not even knowing the block was there and blasting clean through it and making a crater on the surface. And I want to, you know, to better understand and interpret some of the images we're seeing coming back from the spacecraft, it probably is a good idea to actually do some of those experiments and watch how blocks of various, you know, sizes and scales get, you know, transition through that in the gun. So that's part of one of the investigations I'll be doing when we're out there. Plus, it's just fun to, you know, really ram things hard with a big gun like that and make a lot of shots.
So I'm wondering, you know, when Hayabusa first approached Itokawa, I'm wondering if you were as surprised as I was by its appearance. This is a very small asteroid, the smallest one that's ever been visited by a spacecraft. It had a funny kind of cheese doodle shape, is what I thought of it. The Japanese were a little bit more poetical and saw a sea otter.
The sea otter,
To me, it looked like a cheese doodle, but when they got up close, it was covered with gravel.
Yes.
I didn't see soft sort of regolith like you see on a lot of these other asteroids. It was gravel and boulders. Did you find that surprising as well?
Well, I guess in a way, it was I wouldn't say it was unexpected, but it was just, you know, it was a new asteroid. I guess I didn't really know what to expect. That's the beauty of it, right? When you go to someplace new, if you see what you expect, you're kind of disappointed because you really didn't learn anything. So I don't think I had any real preconceptions, but you know, in retrospect, we've come to maybe understand that that's maybe what we should have expected.
That's how it always works.
It's how it always works, right? Yeah, of course we should have known that, right? That's how you learn things. No, what we think's going on there with these little asteroids is, you know, of course the surface is broken up bits of rock and chunks of things because of all these impacts over the eons. It's well, not quite eons for Itokawa; it's too small for that. But it's what makes the on the moon and other airless bodies in the solar system. There are the you know, countless impacts by small impactors that break up and garden the rock on the surface. Even if the surface was originally bare, solid rock, over time, each little impact will crack and pit and crater and leave behind a little bit of debris around it. Some of that's ejected off the surface altogether, but there's always some stuff that's not moving just quite fast enough to escape, and it comes back onto the surface. And that then forms a catchment, if you will, for the next impact to help break up and make more stuff. And over time, you build up this what we call a regolith. It's the soil, the airless soil, without the organics, on the surface of an airless body like this. And over just about the last decade or so, we've really come to this epiphany, this real paradigm shift, that it looks like the geologic processes on the surface of some of these very small objects. We always used to say that collisions dominate the lives of the asteroids, and that's pretty much true, but when you get to these small guys, it really is starting to look like sunlight has an incredibly powerful influence on their evolution. And in many different ways. It can affect their rotations, it can affect their orbits, but in this case, it could probably actually also affect the evolution of that regolith as well, because on these very small objects, as you can imagine, with really low gravity there, when particles are created in these impacts and they want to leave the surface and hang out there, the very slowest ones that are just barely ejected, that kind of want to hang out near the surface, the ones that would reaccumulate back to the surface, the very smallest of those, over those long time scales, it may take minutes or hours to settle back, well, not quite hours, but several minutes to tens of minutes to resettle back to the surface. The action of sunlight operating on some of them can actually blow that stuff away over time. The radiation pressure acting on it can remove those particles before they can actually resettle. And so we think that as we go to smaller and smaller objects with weaker and weaker gravity, the finer particles we winnowed away easier. And so as you go to smaller and smaller objects, before they're so small that you can't have any regolith at all, that regolith may be nothing more than larger chunks of rock and pea-sized gravel rather than dust like we find on the moon. So that's kind of what Itokawa has kind of almost taught us and maybe kind of reinforced for us.
I'm wondering, is this part of what of all of the phenomena that asteroid scientists very poetically refer to as YORP, or is that related but not the same?
It's related but not the same. YORP is an acronym for four scientists, the names of four scientists who kind of had this idea, this understanding that the sunlight can actually affect the rotation rates and the spin pole orientations of small objects in the solar system. So that's an object-oriented sort of effect of the sunlight. You can affect the spin and the orientation. On a grander scale, the Yarkovsky effect, the Y in YORP, there's this other effect called the Yarkovsky effect. It's a more seasonal global effect that can actually affect the orbits, cause the orbits of these objects to shrink or expand, either dive into the sun or move outwards. The key there basically is that just like on the Earth, the hottest time of the day, as the sunlight beats down on the surface rock of these objects, it heats the rock, and that rock wants to eventually re-radiate that energy off to space in the infrared. The hottest time of the day isn't right at noon, it's a little in the afternoon. It takes rock a little while to heat up and come to that equilibrium. And so most of that re-radiating infrared on the surfaces of these asteroids occurs on the afternoon sides. And depending on the direction of the spin, whether the object is spinning in the same orientation that it's going around the sun or in the opposite orientation, that little artificial, well, it's not artificial, that natural, it's almost like a rocket thrust of the infrared photons re-radiating off the surface of the asteroid can either retard the motion of the object and cause its orbit to spiral into the sun, or act to push it outward from the sun over time. So that's the Yarkovsky effect, and it's a size-dependent thing. As you can imagine, that thrust is kind of weak, and so on a big asteroid, it doesn't really do very much. But when you get down to things, maybe a kilometer across and even smaller, like Itokawa, it can become a very important effect in moving this thing around the solar system. And so it's taught us that things can move around the solar system that way. It's taught us that actually that's one way to move the meteorite-producing bodies in the main asteroid belt into the resonances that can deliver the debris to the Earth. It's completely changed our understanding of the dynamics of the small bodies in the solar system. It's kind of a fun time.
Yeah, it's definitely a fun time for sure. I want to pause here for station identification. I'm Emily Lakdawalla of the Planetary Society, here with the weekly CosmoQuest Science Hangout. My host is Dan Durda of the Southwest Research Institute. He's an asteroid scientist, as he's been discussing, but he's also a space artist, and we'll get to that a little bit later. I also want to mention to those of you who are watching this, I want to ask you to either +1 it on Google+, or give it a thumbs up on YouTube. And there will be some time toward the end of this broadcast for questions. So if you would like to start thinking about your questions, I'll be looking for them in the comments on the Google Plus feed, or on YouTube, or via Twitter. If you reply to my Twitter link about the show, then I'll look in all three of those places for questions toward the end. But I think, Dan, before we get to art, I would like to at least mention a project that the Planetary Society and you worked on together that had to do with these elusive things called Vulcanoids. I wonder if you can talk about what Vulcanoids are and whether they exist.
Oh, absolutely. It's great. Yeah, in fact, we have a history together on that, the Planetary Society. When I first arrived here at the Southwest Research Institute back in the late 90s, we got this idea to sort of revamp this search for this potential population of small asteroid-like bodies that might be in stable orbits, interior to the orbit of Mercury, really close to the sun. If you do, again, these dynamical models, these simulations of the orbital evolution of these little things in the solar system, there aren't many places in the solar system that are stable over the vast times over the entire history of the solar system. You get anywhere near any of the planets, and things get perturbed and stirred around, and they get ejected from the solar system or collide. And there are only a few places in there between the planets where you can find these stable zones. The main asteroid belt is one obvious example. That's why it's there. But the calculations suggest that interior to Mercury, there is a range in there where you might actually have stable particles existing since the planets came to be. So people had been looking for the potential objects in this region for literally well over a century. They're called Vulcanoids because the first indication that there might be something there was the orbit, the changing nature of the orbit of the planet Mercury itself. Before Einstein's theory of general relativity that was able to explain through the gravitational perturbations from the sun these weird motions of Mercury, people thought perhaps there might be a little planet interior that was perturbing Mercury's motion, and that putative planet was called Vulcan because of its proximity to the sun. And when the reason to have a planet Vulcan went away with general relativity, the thought occurred that there may still be even small stuff still in there that are even smaller that might exist. And the term was they threw the term Vulcanoids at these putative objects. But searches over the previous century didn't find anything. But they weren't very constraining searches. And so we had this idea to actually go back and look at data from the SOHO spacecraft, which is studying the sun, but because it's studying the sun, it's also looking in the vicinity very well. We thought maybe the coronagraph on SOHO would be a good way to block out the light of the sun and look to see if there were any faint objects back there. We did a pretty good constraining search, didn't find anything down to about 8th magnitude, but that still left the possibility of some small objects there. And so over the years, we've been thinking of other creative ways to crack that problem, from airborne investigations in the back seats of F-18s, which we flew back in 2000, 2002. But also around that time, we were getting ready to fly a conventional sounding rocket experiment out of the White Sands Missile Range to study the planet Mercury in the ultraviolet. But that rocket was capable of carrying a lot more payload than was taken up by this ultraviolet spectrometer. And so we attached a camera in there with some help and funding from the Planetary Society to just a broad area imaging camera to, as long as Mercury was looking, or the rocket payload was looking at Mercury, we let our camera look off to the side to see if there were any potential Vulcanoids there. And again, we didn't see them in those data, but it was a great opportunity to work with the Planetary Society on a pretty out-of-the-box idea. And that's what it takes sometimes to solve some of these problems, just to think out of the box and try some new solutions to things. So.
And I think Messenger has did a pretty exhaustive search for the Vulcanoids while it was on its cruise to Mercury, and also, unfortunately, did not find any of these.
So it's, you keep looking, after time it starts to make you wonder. I mean, the very most constraining search we've just completed, I think it's the best search that's ever been done and likely will be done short of having a dedicated telescope for something like this. We've actually used, similar to the SOHO observations, we now have used the coronagraphic observations from the Stereo spacecraft. And that's taken us down to much fainter magnitudes. We did about magnitude 8 with SOHO. We are now with Stereo. We're finding, magnitude 13 little main, in the background, main belt asteroids moving out there in the background. We're seeing these, magnitude 13 objects really close to the sun. That puts us down into the region where, that's like, 5 or 6 or 7 kilometer across Vulcanoids. And so we haven't found any to that level. It's starting to look like maybe these sort of radiation forces like the Yarkovsky Effect have probably removed objects at that scale. It's not conclusive yet, but it's starting to really aim in that direction, I think.
So the project that we helped you do is using a sounding rocket, which is a suborbital flight, and I know that you're still very interested in doing suborbital research, so I'm wondering if you want to tell us a little bit about that.
Yeah, absolutely. We have a project here at Southwest Research Institute to take advantage of this what we call next generation of suborbital vehicles that are being developed for in the commercial industry out there. Initially, at least, primarily for the purposes of adventure tourism. This is the Richard Branson with Virgin Galactic and a handful of other companies out there, Blue Origin and Xcore Aerospace and Armadillo and Maston. All of these companies are building vehicles to make the payloads us, which I think is absolutely fantastic. It's for you and me to go and experience effectively the flight that Alan Shepard made in the first flights to space.
And you in particular, I think you have a ticket, right?
And we in particular here at Southwest, I'm one of the 3 payload specialists here at the Southwest Research Institute. We have 6 seats purchased with Xcore Aerospace and 3 seats purchased with Virgin Galactic. And so one of the payloads will be me, and we'll get a chance to actually get up there and see the curvature of the Earth and the thin blue line, awesome. And get that experience. And it's what's even more awesome than that is that you and people watching this and linking to it are going to get that chance too. It's not that I'm all that special. That's the beauty of this next generation of vehicles. It's going to drastically, and I mean drastically, change the ability of having frequent and low-cost access to space for people like you and me, not just healthy, fit test pilots who get to be government employees and fly vehicles to space. It's a chance for all of us to get to go and do this and experience that. So it's going to really revolutionize the way all of us get to interact and think about what you can and what you can do and imagine doing in space.
And I think that's a perfect segue into what we can imagine might exist out there in space as represented in space art. So I'd like you to talk about what you do and why and what inspired you, and maybe show us some of your stuff.
Sure, I'd be glad to. It's a passion. It really is. I love. I mean, it's science and art. How do you do the both? Is one so left brain and the other very creative, and one side very analytical and the other and science, I want to remind people that the tools of science, the bits and pieces that we use to accomplish doing the science is the sort of the left brain, very analytical side of things. But the process of science is exactly that same creative right brain enterprise that is art. And so it shouldn't be surprised that it's the same sort of thing.
I certainly find among scientists to be some of the more creative people I know, and it tends to get expressed in a lot of different ways. In
music and
exactly.
Yeah, all kinds of things. And so for me, it comes out in artwork. I can't say that I had the same sort of lifelong interest in artwork like I had in science growing up. I mean, I doodled as a kid. I did charcoal sketches of antelopes and things like that, just because I was interested in playing around and doing fun stuff. But really, for a number of years, I didn't do anything like that until I moved to Tucson as a postdoc. And Tucson is the home of Novaspace Gallery, run by Kim Poor, a rather well-known space artist. And having now moved to the local area, I thought it'd be kind of fun to go visit this gallery in person. And as soon as I walked in the door, I was just absolutely, jaw to the floor, stunned at the beauty of seeing this artwork in person. If you're a fan of art, you know what it's like to finally see the original of some piece of artwork that you've admired over the years, only in seeing in reproduced form in like a poster or something like that. Just nothing like seeing the original. And that experience just floored me. And so for some reason, my reaction to that was, I wonder if I can do this myself. I don't know why I had that reaction, but I had that reaction. So I literally, with zero formal training whatsoever, just went to the craft store, started buying some paints and media and things, and just started doodling around and learning a few things here and there. I had the benefit that I was right there local. I could take things to show Kim. I had also the great benefit that one of my science colleagues, Bill Hartman, is also an incredibly accomplished astronomical artist. And so between Kim and Bill encouraging me and giving me examples to learn from, that kind of very, very quickly developed. I joined the IAAA, the International Association of Astronomical Artists. Bill and Kim encouraged me to attend that first workshop back in 1995, and it's all been a fun journey ever since. I think you have maybe a good segue to that set of files that I sent you.
I'm gonna try sharing the PowerPoint presentation.
Yeah.
How that works.
Yeah, let's look at some pictures. Mentioning the IAAA, here are some of my friends from the IAAA, the International Association of Astronomical Artists. Actually, this organization was born partially because of Planetary Society. Back in the 1980s, to help popularize and show off the great, exciting results from the Voyager encounters. I think it was the first Planet Fest was started back in 1981 as Voyager was getting off to Saturn. And associated with that first Planet Fest, many of the artists who had been working either together or just separately and not knowing it on Cosmos, on some of the artwork for Cosmos, they got together at Planet Fest back then to it was just, for many of them, it was a fun experience to get to know that there were other people who thought the way they did and had the same excitement that they did. And so they formed this little nucleus of a new organization. If we go to the next slide, that kind of shows, I think, their excitement after 1981 was, let's see if we can get together again and actually get together in the field and go to places that are kind of like other planetary environments and do some art together and build from this little core group that we've started. So back in 1982, they went to Hawaii and decided, let's formalize this and actually form a group. And These workshops have continued, 1984 off to Death Valley, and there's a little humor in some of this. This is, again, we mentioned creative people, and of course some of the humor that gets imposed in some of these things. Joel Hagen, one of our more creative members, and they were walking around the amazing colored sands and things that are there in Death Valley. He got the idea to put up these fake signs all over the valley that were warning that these colorful sands are actually mixtures of flammable chemicals, and it was a big practical joke they played on actually the rangers and all the other public that were attending. And so I wasn't there for this, but there were reports of people standing there smoking, reading these signs, all of a sudden rapidly putting out their cigarette butts and things to be sure you didn't set fire to the desert out there. But the rangers quickly caught on and started tearing down the signs. But it was a fun joke while it lasted, but create a group of people. So it truly is an international organization. We have, I don't know, between 150, 200 members literally spread around the planet. We get together in, as you can see, some of these workshops we've been showing you. They're not all here in the United States, but I guess just by random luck of the draw, I'm showing you some of the images from places like Grand Canyon. And the reason we go out to these places is to learn from nature. To if you sit there and draw things in the studio all the time, after a while your rocks start to look like piles of mashed potatoes, because you forget what real rocks look like, right? And what real craters and what real mountains and how light bounces off of things. And so we find that it's a really fun time to get together, go out to these environments, and remind ourselves what they look like in reality. And here's a great example on that. Just go back one. I just want to show you this. There's one of our artists painting in front of Ubehebe crater at Death Valley, and below that.
Down inside Ubehebe crater, it's very easy to get down and very, very hard to get back up.
That's right. Just like the Grand Canyon, you're so easy to tempted to start hiking down, you forget you have the trip to go back up. Below is a painting of that very same crater done by Mike Carroll, who used the crater as inspiration to turn this into one of the volcanic vents on Jupiter's moon Io. So again, this is inspiration for some of the just absolutely wonderful art that you've all seen over the years, as artists have gone out and explored and rather much the same that the Hudson River School of Artists went out west and painted the glorious views of the western frontier that was being reported back as the explorers there were coming back and inspiring people to travel out west, and actually inspiring the formation of the first national parks. So in a lot of ways we as space arts are helping visualize and inspire that exploration in this generation. So it's a lot of fun. So we have the IEEE. The next slide I think is just a little picture kind of guide to go to our website, the IEEE.org. Go visit. We have a wonderful book there of the artwork from our members and telling the history of the organization and a little bit of the techniques of the organization of the artists. It's called The Beauty of Space. It really is
a cool book. My only complaint about it was that it contains so much art that it's reproduced a little bit small. But there's really a lot of great stuff in there.
It's a fun book. So if you're a fan of space art, definitely go to that book. My own journey through artwork has transitioned from the traditional sort of techniques of acrylic paint on canvas or illustration board. I'd already been dabbling a little bit with Photoshop to start playing some games with moving things around and doing some things in Photoshop that I couldn't do with the traditional techniques. But all of that was just mere dabbling. I continued to paint traditionally until about 2.5 years ago. There was this movie, some obscure movie about tall blue people that came out that just absolutely changed my life.
I understand you only saw that just a couple times.
Just a couple. Jim Cameron owes me a lot of money because I helped sink Titanic in box office sales. I saw Avatar in the movie in IMAX 3D 15 times, and the only reason I didn't see it more was I basically ran out of time. The movie left the theaters before I could continue watching it. So if it's ever re-released, I'm going to see it a lot more times in the theater as well. But no, that movie, what Jim and his creative team did with that movie just blew me away on every dimension of my interests that I can possibly imagine. It was as a scientist interested in extrasolar planets and visualizing the environments of these worlds, but as an artist trying to visualize them. They did everything in that movie that I'd always been wanting to do, and they did it the way I wanted to do it, which is as photorealistically as possible. So it really pushed me over the edge to you know, go digital basically and start learning these techniques. Over the last 2 years, it's been this just passionate journey of discovery of learning all these digital tools. As you step through here, a few of these slides will show some of the, you know, the new things I've been able to learn to do with the digital tools, and representing some of the things that I couldn't do just because I'm not a talented enough artist traditionally to do. But you can see a common theme. Ah, hey, that looks kind of familiar from yesterday in a way. This is a piece I did actually to illustrate what I think is coming pretty soon from what I think is probably the hottest mission that NASA's got going, which is the Kepler mission, which is responsible for finding all of these thousands of planets around other stars. And I think coming soon will be the day when we've discovered the first exo-moon. Some of these moons around some of these planets are large enough to be considered planetary worlds in their own right, and Kepler is maybe just good enough to start picking out some of the signals of some of the larger moons amongst the data. And so I did this image to kind of hint at what that, you know, kind of suggest what, you know, what the systems will look like that the data that Kepler will be returning will tell us about. So,
you know, I want to pause there to talk about exomoons, because I'm wondering if you tend to be as irritated as I get when people talk about habitable zones around other stars, because, you know, Earth is in the so-called habitable zone, but we talk about life being possible on Mars and even on Europa, which is way farther away from the sun. And I think that, you know, our imaginations are not, or other people's imaginations perhaps, are not spreading quite far enough to think about the possibilities for life on 10 or 12 different things around each of these stars that we think there are 10 billion stars that might have planets around them.
Absolutely.
That's my little rant about that.
No, I agree with you completely. Nature is so much more inventive than we can possibly be, paraphrasing one of our more famous sci-fi literary people. And you'll notice that a lot of my art has got that sort of a theme of the moons being habitable, not so much even the planet themselves, but the moons. And part of that is a bit of an artistic cheat, just because it makes the skies a little prettier if I can have a big planet up there. But this is an obviously somewhat Avatar-inspired image. Actually, this was more of an experiment to see if I could reproduce the sort of self-luminous effects in one piece of software that I drive quite a bit, and that was a bit of an experiment. But it was also just a fun thing to, you know, it's not just the moons, it's the biology of these worlds. This is an image I did to help promote the concept of a U.S. postage stamp that we're trying to propose to the U.S. Post Office to commemorate the New Horizons flyby of the planet, my conceit, of the world Pluto out there in 2015. So Alan Stern asked me if I would do the artwork for this proposal to help promote that. That was a lot of fun to do. I want to step on, I think there's always a fun thing about, you know, how do you do this? And so I put together some slides here to very quickly step through. I don't want to dwell on these too long, but just to step through how I do all this stuff. It's hardware, it's digital, and so I got a fairly decent computer. I use one of these light pads. It's a tablet that you actually draw on the screen as you're doing your artwork.
That's very cool.
It has really revolutionized for me my ability to sort of handle and do all this stuff. And I've got this down in the bottom right corner there, that very largest Cintiq. It's the 24 HD. The screen. It's like working on a big electronic drafting table, and it's just sheer joy. Use a lot of different software packages. One I use a lot is called View. It's one of these ones that's really good at generating atmospheres and taking care of the lighting of things. I think the next image shows a little bit how it's very good at doing ecosystems and grass and organic things. This is what it looks like inside the program when I'm working on one of these scenes. You get sort of a top view, a side view, a left side view, and then a camera view of what the scene is kind of looking like as you're building it up. So that's kind of what you see as you're working. But then, you know, remember, this is all pure mathematical and digital. This is what you see pop out the other end. There's no photographic elements in there. This is all just pure mathematical, pushing pixels around. This is the CPU calculating how the light bounces around and reflects on other objects, and camera defocusing and all that kind of fun stuff. It's just amazing to me still that this stuff works. Here's a, you know, View generates, you know, landscape-like terrains, but it's not very good at erosion. And so I run view, stick it into another code called worldview, and then pop it back out to actually generate a more realistic looking eroded terrain. So it's
Dan, before you, I think it might be great if after this conversation is over, if you could send me an email with the names of all of these things. I'll drop it into my blog entry about this Hangout, and then people can actually follow up on the stuff that you mentioned.
Sure, yeah, absolutely. Because a lot of some of these things are free or very cheap. Some are a little bit more expensive, but there's a lot of free options out there as well for this. I use XFrog for making a lot of alien plants. I can generate any kind. I can build and generate together any kind of plant form I want to do. I use. I think the next slide is my one. Well, actually, I think the next slide actually just shows an example rendered out of what one of these built plants would look like. In
this one.
Yeah, it kind of froze there. I don't see it updating on my screen, but
oh, okay.
I'm still seeing an XFrog thing there. So we skipped one. That's okay. Don't worry about it. That's fine. Okay. We skipped the slide that shows Photoshop. I just want to put a plug in. I could not live without Photoshop. Here's the Photoshop slide. It's just a window showing Photoshop. I use it for everything. I use it for actually drawing and altering things. I use it for compositing together pieces of other bits I've done in other things. The next 3 slides show that kind of step of how I composite together. Here's just a little watery world cratered thing I generate in Celestia, which is a free public domain thing out there. Celestia, I like the atmospheres I can generate in View a little bit better, so I generate an atmosphere in View. And then next slide, I just composite it all together in Photoshop and generate some exomoons and different views of things. Here's another step-by-step through. This is a photograph, raw, complete photograph out of just straight from my digital camera, complete with dust marks because my sensor was dirty, out at Kennedy Space Center the morning after one of my zero-G flights. We don't have any beaches in Colorado, and so I wanted to use that image as a base reference for some artwork. I wanted to do something a little bit more special, so I painted out the sky, erased everything I didn't want, used View to render in a new, more slightly alien-looking sort of terrain. The sky was boring in the original image, so I rendered a sky, the sun and the clouds, to be a little bit more interesting. Threw in a planet coming up here, the next several images, some moons go in there, some sort of alien birds and their reflections on the water, and then after a while you can build it. It's a very similar process to the way the effects are done in a lot of these Hollywood movies. Any special effects scene you see in any of these movies is not just one wholly rendered thing all by itself. There are many, sometimes hundreds of separate elements in a particular scene that are then composited together. Here's that very same beach at Cocoa Beach, just a different time of the day with a different set of rocks digitally rendered out, and then their reflections added into the water, and just shows the power of what digital is allowing me to explore. I'm doing the art I like to do. I don't know if other people like it, but I'm doing what I like to do, and I'm having a heck of a lot of fun doing it.
I think that's what being an artist is all about, though.
That's right. That's right. Thank goodness. And so my latest piece I just did about a week before Space Fest. I was furiously churning this out before I was leaving for Space Fest. Back to this whole idea of the IAAA going to these fun places. This is Mars Hill, aptly named, in Death Valley. And in fact, this is a panoramic sequence assembled together of a sequence of images I took on one of our space art workshops out there back in 2005. I color shifted the things to match the Martian colors, took out all the weeds and grass, digitally added in some astronauts and a landing craft out there, and pretty soon we brought we went to Mars by just being out at Death Valley, and hopefully making an inspiring vision for people to think about what we can really go out there and do in reality. And that's what space art is all about, is helping imagine sometimes almost the unimaginable, but at least the sometimes unreachable, and inspiring us to go out there and explore ourselves. And that's the beauty of space art and the joy of hanging out with all my space art colleagues, because they all sort of have that like way of thinking about things. So I'll leave it at that, and hopefully folks have some questions about that. Or
yeah, so let me pause here and say again, this is Emily Lakdawalla with the Planetary Society on the weekly CosmoQuest Science Hour, hosting Dan Durda of the Southwest Research Institute, who's an asteroid astronomer, scientist, and modeler, as well as space artist. So I'm now looking for questions. I am looking for questions either on the Google Plus page, and again, I hope if you're watching it there that you give it a +1, or on the YouTube page for this, and there please give it a thumbs up, or via Twitter, if you could just @mention me and send me the question. I would be happy to give any questions that come up to Dan. I actually don't see any so far, so jump in there if you've got any questions. Oh, here we go. Here's one. So Ciro Villa asks, Dan, in your opinion, what's the most promising and realistically obtainable technology currently in development to assist in the deflection of dangerous asteroids on a collision course with planet Earth?
Very good question. We didn't talk about that in terms of the near-Earth objects that way, but a big part of what the Planetary Society does, too, is assist in this cataloging and characterization of these objects in this population that could potentially harm us. Those are the first two steps. Find them, then catalog them. The next step is, if we ever do find one that's on his way to hit us, is to actually go out there and do something about that. The dinosaurs went extinct because they didn't have a space program. Luckily, we're in a little bit better shape than that. I think there have been a number of ways proposed to actually go out there and stop an asteroid from impacting us. The most common Hollywood solution is to go out there and nuke it to bits, right? You just blow it to smithereens.
Because everything can be solved with explosions.
Because everything can be solved with enough firepower. That's actually pretty much the last thing you want to actually do. It's a rather uncontrolled way to deal with the problem, and we don't know that we might not actually make the problem worse. It's not that, you know. Well, anyway, so one technique that actually does work, though, is nuking the asteroid, but not by nuking it to bits. What you would actually want to do, if you were to deploy this sort of technique, is to use what we call as a standoff device. You don't actually drill into the asteroid and blow it up from inside. You actually would detonate the device above the surface, just out in space, just off the surface of the asteroid, so that the flux, the radiation, the neutron radiation from the blast itself would actually vaporize, volatilize off the surface the materials on the surface that are easy to evaporate, whatever water might be there, whatever other light minerals in the rocks that are easy to get off there. And what that does is it acts as carbonaceous stuff. It acts like a little artificial cometary jet, like a little rocket motor on the side, that would nudge the object off its collision course with the Earth. Doesn't take much nudge. If you do this, 10 years ahead of an impact, it only takes maybe fractions of a millimeter per second change in the orbital speed of the asteroid around the Sun to miss its appointment with the Earth, decades hence. You turn what would have been an impact into a near miss.
And the Planetary Society is actually studying a little project called mirror bees or laser bees, which would do effectively the same thing. It would collect sunlight, turn it into a laser, and use that to volatilize the surface.
And use that
so it's basically the same approach.
Yep, basically the same idea. So there are a lot of nuances to that general idea of vaporizing off the surface. The most violent of which tends to be the nuclear thing. In a lot of ways, I think it would work, but we really probably want to save that for our last resort because it's not really a controllable method. We don't know that we're actually going to move the object in the direction or by the amount we really need to. And so we want to use something like a more controllable method. And moving in the direction of more controllable would be something like a kinetic impactor, kind of like what we did in small scale with the Deep Impact mission at it was Temple 1, was it not? Mm-hmm. Yes, it was. That was the focus of that mission was to study the physics of the surface of the object, but the same technique of slamming a spacecraft into a targeted impact with one of these objects could accomplish the same sort of speed change to the object decades ahead. That's moving in the direction of being controllable, but even that, though, still, if you don't get it just quite right, you're not sure you're going to get the job done exactly the way you want.
I think that when we looked at the physics of the deep impact, which I hate having to say, but I can't think of any other way to describe it, is that don't they think that the impactor actually penetrated quite a great distance into very loose stuff before its kinetic energy was imparted to the comet, and that's partially what produced this strange, almost there's like a jet that came out.
Yeah, a little more focused cone of ejecta, if you will. Yeah, and that's cool because it tells us about the surfaces of that particular cometary object. It does look like it penetrated through a little bit more of a kind of almost like a more crusty, dehydrated layer of dusty stuff before it actually left most of its energy in the surface of the comet there. So that actually is an interesting. What happens if the object we try to deflect is very much more porous inside than we anticipated, and the energy of the impact is is absorbed more into the surface, and the spray of cratering ejecta is not as great as we thought to carry that momentum away from the object, and actually is what accomplishes the push in that technique. This is why these kinds of experiments are very, very important for us to do before it counts. The last thing we want to do is actually have to go out there and deflect one of these objects one day without having actually done enough of the legwork ahead of time to understand what works and what doesn't. That's how you learn. So so let me just end with probably I think the most elegant and controllable method of doing this sort of thing, which is the gravity tractor. It's this idea that you can park a massive spacecraft, not that massive, maybe the mass of a communications satellite, next to the asteroid. Hover next to it. Don't let the gravity of the asteroid completely pull the spacecraft down onto its surface. You just hover off the surface using very low thrust but long duration thrusters like ion thrusters. And then you're effectively, the gravity of the spacecraft on the asteroid is attracting the asteroid to the spacecraft. If you do that just right and in the right direction and by the right amount, you're effectively using the gravity of the spacecraft as a tow line to gently move the asteroid off its collision course. And again, if affected decades in advance of an impending impact, it only takes tiny, tiny fractions of a millimeter per second change in the speed of this thing around the sun to make it miss the Earth. And that's really what you want to do. And the beauty of the gravity tractor is that you can precisely control the direction and the amount of that change in speed. And so I think a great technique might go in there to use the power of a kinetic impactor to do most of the work, and then use a gravity tractor to monitor the change and affect the fine-tuning. I think that'd be a very powerful combination of doing things, and I'd love to see a demonstration mission someday in the future to do just that.
Well, Dan, I think that was such a good question that it's kind of rounded out the rest of our time. So I think we're probably going to go ahead and close here. And I'm also closing it because I just saw a random Google Plus error. And I know not to go too far beyond those because things can suddenly break. So again, I'm Emily Lakdawalla for the Planetary Society. You've been watching the CosmoQuest Weekly Science Hour on YouTube or Google Plus. And again, if you could please +1 it or like it on YouTube if you've been watching, even if you're watching it delayed, as most of you probably are. Thank you very much for your attention. I thank Dan very much for taking the time to talk with me today. It's been a delightful conversation. I think we're going to have to do this again sometime.
Thanks, Emily. It's been a lot of fun.
You will, I'm going to ask you to send me some information about the software that you use for your space art, and I'll put that in my blog post at planetary.org/blog, so that those of you who might be interested in taking it up yourselves can try out some of the, especially the free tools that he mentions. Although I too love Photoshop, as expensive as it is and as hard to deal with as it sometimes is, there's really no replacement for it. I've tried GIMP, but Photoshop is really where it's at. Anyway, thanks so much, Dan, and I look forward to doing this again.
Me too. Thanks a lot.